So while we started talking about motion in the last video, we need to remember that this unit is called Kinematics of Graphical Analysis. So now it's time that we actually start looking at some graphs and what exactly we can get from them. Specifically, uniform, and I'll talk about what that means in a bit, position versus time graphs, and uniform velocity versus time graphs. To start off, let's look at an example. Let's say you and your friend are bowling. And so you're going to throw the balls down, they're going to roll down and hit these pins at the end. And if you look here, we actually have a nice little number line going from 0, 1 meter, 2 meter, 3 meter, 4 meters. So our 1D motion will be down the bowling lane. And let's say you both let go of your bowling balls at time t equals 0 seconds. You release yours at the 0 mark, but your friend is a little bit of a further step behind, and they release it at, we'll say that's about the negative 0.5 meter mark. But then the balls start rolling forward, and at 1 second, yours has only made it 1 meter, but your friend, who apparently works out a bunch, has gone 2 meters to position about 1.5 meters. Then at 2 seconds, yours has made it 2 meters, theirs has made it all the way to 3.5 meters. Then at 3 seconds, your friend's ball has already hit the pins, and at 4 seconds. So first off, what we call these type of diagrams here, there's actually a specific name for them, are motion diagrams. Basically what they're showing us is snapshots of the motion at different points in time. So first off, we have this snapshot here at 0 seconds, then we have a snapshot at 1 second, 2 seconds, and then the snapshot at 3 second and 4 second really only show the green ball because the pink ball has already reached the end. But now we want to move this motion diagram into a graph. And the first type of graph we're going to look at is called a position versus time graph. So we have our position with unit of meters on our vertical axis and the time in seconds on the horizontal axis. And let's actually rewind a little bit here and see where we started. So at time t equals 0, let me go ahead and get a different pin here. At time t equals 0, your ball starts at the 0 position. Your friend's ball starts at about negative 0.5. So at t equals 0, these are their two positions. At t equals 1 second, we now move forward to 1 second, and we say that your friend's was at about 1.5, and yours is at about 1. At 2 seconds, we move forward to 2. Yours is now at 2 meters, and your friend's is at about 3.5. And then at 3 seconds, yours is at 3, they've already passed on. And at 4 seconds, yours is at 4. Okay, so a couple things here. We want to be real careful that a graph is a two-dimensional space, right? We've got an axis here and an axis there. We're creating it on a plane. But remember, this is still only one-dimensional motion. So they're only moving in positions showing this way. This is time here. It's showing us forward in time. So each one of these we can treat like a snapshot. So this was kind of what it was like at 0 seconds. Theirs was behind yours. At 1 second, they've already passed you. At 2 seconds, they're way behind you. And then at 3 and 4. And if I want to make these look real nice, I can change them into graphs. So I'm going to start here, roughly, and go up through these points. And then for yours, we'll use green, and we'll start here and try our best to line up, a little bit off, but that's okay, through those points. And what is this showing us? Well, there's a few things we might notice. One, we have different y-intercepts. We'll talk about what that means in a second. 2, we have different slopes. Specifically, your friend's slope is greater than your slope. So what does that mean? And 3, what is happening at this point here? Well, let's go ahead and say that one right now. But what's happening right here, well, this is the point when you both had your balls had the same position. So therefore, this is really the point when the pink ball is passing the green ball, which happens sometime between 0 and 1 second. So sometime back here, which makes sense. So we just constructed a position versus time graph. And we want to be real careful here that since it's position versus time, that is x versus t. And remember from back when we were looking at graphs that this, since it's in front, means it goes on the vertical axis. So t is going to go on the horizontal axis. And that might trip you up, because that means x, or position, is going on the y-axis, which is why we typically call it the vertical axis instead of the y-axis. So we're going to have x on the vertical axis, t on the horizontal axis. We know t is the independent variable because no matter what you do, you can't affect it. As time moves forward, the position changes. The position depends on how much time has passed. All right, so let's look at a couple things here. First off, we were talking about, well, what does this y-intercept mean? Well, that is the position at time equals 0. Well, that is going to be your initial position, or x naught. So if you look back in the previous one with the bowling situation, yours had a initial position of about 0. Your friends had initial position about negative 0.5 meters. They started behind you. The other key piece of information we want is the slope. So let's say we find 2 points on this line, and we say this is t1, x1, and this is t2, x2. And if you were going to find the slope, we would say that it is what? Rise over run. So it would be x2 minus x1 over t2 minus t1. But this is no different than delta x over delta t. Well, that looks really familiar, and that's because this is the equation for velocity. So the slope of this graph is actually telling us the velocity. And so in the previous graph when we were looking at, your friend's graph was steeper because it had a greater velocity. It was moving faster than yours was. And additionally, if we want to double check this, well, slope, okay, remember the units are rise over run. Well, the units would be meters over seconds. That's a unit of velocity. It makes sense. So if we were going to write an equation of a line like this, remember we have to replace quite a few things. Instead of y, we would have x. Our slope would be velocity. Our x would now be t. And our y-intercept is now the initial position. So this is the format of how we would write a basic equation for a line on a position versus time graph. Keeping in mind that's just for a straight line. If it starts bending or doing anything like that, it starts no longer working. But this shouldn't be surprising anyway, because if we look, let's make this black here. If we look, well, let's rearrange this. If I subtract the x naught, x minus x naught equals v times t, I divide both sides by t, so I do over t, get rid of that. Well, v is equal to x minus x over t. That's just the equation for velocity. So this equation of a line is really just the velocity equation rearranged into a different format. But this is one of the most important pieces of information in this whole video. We just learned that the slope of x versus t gives velocity. So no matter what, if you look at the slope of a position versus time graph, whatever information you get from that slope tells you something about the velocity. These are deeply tied together. Just so you know, if you're in calculus, it's because the velocity is the derivative of a position versus time graph. Okay, so now let's look at this for a second to give you a couple of examples. So for instance, let's say that we had something like this. Well, that is a constant slope. It never changes. It's a positive slope. So that tells us that the velocity would be constant and it would be positive. So it's not changing and it's moving in the positive direction. Similarly, let's say we had a velocity that looks like this. Well, that is constant but a negative slope. So this object is moving at a constant rate in the negative direction. Well, what happens if instead it just looks like this? Well, what is the slope? Oh, let's change that. What is the slope of a flat line? Is just 0, which means that the velocity is 0, therefore it is at rest, which makes sense because this position isn't changing. Now, one last thing I do want to say is you could have something that starts bending like this, and if that's the case, the velocity is changing. It's speeding up and slowing down, but we're not going to be looking at that quite yet. Now, this is a typical example of a position versus time graph, and we're looking at the object as moving in a time interval from 0 to 50 seconds, and a bunch of different things happen. You'll notice we've got really 1, 2, 3, 4 different segments. And we need to make sure that we can interpret what exactly is happening here. Okay, now first off, remember, this is actually happening on a number line. It's really just one-dimensional motion. This object isn't going up a hill and then down a hill. It's just moving forward and then moving backward and then forward again. So a few things to note. The initial position is 0, so it would be starting here. It then moves forward during 10 seconds to 60 meters. So it's going to go all the way to 60 meters. And then it stops for 5 seconds because there's no change in position. It's then going to go backward all the way to negative 40 at 40 seconds. So it's going to go backward all the way to negative 40. And then it's going to move back forward immediately back to its starting position. So that's what's happening here. So it's going forward, stopping, moving backward, then back to the start. And specifically, we already got the initial position, but remember the slope also tells us the velocity. But we have a bunch of different slopes here. They're all constant, but they're different. Now I'm going to go ahead and pull out my calculator. I encourage you to do the same, and go ahead and calculate what these 4 different slopes are. Good practice. So go ahead and pause. Go do that, and I'm going to quickly do it all together. Okay, so this first slope here, we should be getting 6. So this would be, the velocity is 6 meters per second, positive. Here the slope is 0. And this region, there's a lot going on, but this slope is negative 4 meters per second. And lastly, this slope here is positive 4 meters per second. One last piece of information we want to really briefly highlight is what is happening here. Well, the object hasn't stopped. It's only at rest when the slope is 0, so it's still moving, but what happens here when we're at 0, oh, we've just returned to our starting place. So that would be this point, it's gone forward. That would be happening right here as it continues to move past its starting point before coming back to the 0 location. So we started with this position versus time graph over here, and remember this was 6 meters per second, 0, negative 4 meters per second, and 4 meters per second. Those were my slopes and therefore my velocities. And now we want to create what is known as a velocity versus time graph. It's very similar to a position versus time graph, but now we're looking at a different part of the object's motion. We don't care about the position anymore. Now we care about the velocity. So you need to make sure you pay attention to what is on this axis. That's probably the #1 mistake I see people make, is they get these mixed up because they don't read the axes. Before you do anything, pause, read the axes. Okay, so from 0 to 10 seconds, it's moving at 6 meters per second at a constant rate. So from 0 to 10 seconds, we want to be at 6 meters per second. So we're just going to draw this here. There we go. From 10 to 15, we're at 0. From 15 to 40, we're at -4. And then from 40 to 50, we're at 4. Okay. Now one quick note here. You'll notice we're going spontaneously from 6 to 0. Now is that realistic? No, but it's helping us analyze this a little better. So if you have an immediate jump in velocity like this, we don't usually draw it as a straight line. We usually draw it as a dashed line to let us know, oh, we've immediately jumped from one velocity to the next. But the key thing we need to know is that these two graphs are representations, visualizations of the exact same motion. This is the same object in this graph and in this graph, but they're showing us different information. Specifically, these are multiple segments of what we call uniform motion, and by uniform, what we're typically referring to are constant velocity, aka you go at some constant velocity, then you change to a different constant velocity, then you change to a different constant velocity. That's what we mean by uniform. It's not constant the whole time, but we have different segments of constant. So now we have velocity versus time graphs. And remember, once again, velocity is in front, v versus t, so v needs to go on our vertical axis and t on our horizontal axis. So this is the exact same graph we just created on the previous slide, but let's talk about a couple things here. First off, just like for the position versus time, this y-intercept here is going to tell us the initial velocity. That is the velocity we start at. So that's a good piece of information we want. And if we look, all these slopes are 0, so we're not getting anything from the slope here. But in the last slide, we moved from a position versus time to a velocity versus time graph by using the slope. How can we take this graph and move back to a position versus time graph? Because occasionally we will get that. We will have this information and we want to know what the other information looks like. Well, how exactly can I do that? Because there's no slopes here to consider, so what should I be looking at instead? Well, remember that the equation for velocity is delta x over delta t. And if I multiply this delta t across, I get v delta t is equal to delta x. But how can I get v delta t? Let's look at this first little segment here from 0 to 10 seconds. How can I get v delta t from this part of the graph? Well, delta t is right here, right? That's our change in time is 10 seconds. And our v goes from 0 to 6, right? Because this is what our initial velocity is. So if I want v times delta t, well, look at that. That would be that area. This area will tell me v delta t, and therefore delta x. And specifically, what would this area be? It would be 6 times 10, so it would be 60, and I had meters per second for the velocity, times seconds. So times seconds, I would get rid of that, 60 meters. Okay, well if I look in this section, there's not really much going on, we're just at rest. Looking from 15 to 40. Well, once again, let's look at v. v is minus 4. My delta t is, let's see, 10, 20, 25. So my area here would be 25 times negative 4 is negative 100 meters. That's my delta x. And lastly, I have this section here, and this actually should be going all the way up. I drew that wrong. All the way to there. And I would have 10 times 4, so this would be a delta x of 40 meters. So this is the other big key information we want to make sure we get from this video, is that the area under, and we'll talk about what that means in a second, a v versus t graph gives delta x, or the displacement. Okay, so let's talk about what I mean that. First off, let's look in this first section. The area under means the area between the horizontal axis and the graph. So it would be this area here for this first segment. And that area is going to be 2 times 2, so this would be 2 times 2 is 4 meters. Well, there's no area here, so this would be 0 meters. And lastly, I'm going to go between the 0 and the graph. So this is not really under, this is kind of over, but it's the area between the horizontal axis and the graph. So it's going to be this area here. Tells me that this is a displacement of minus 4 meters. So if it is a positive area, aka it is above this axis, that will be a positive delta x. If it is a negative area, it is one of these below the x-axis, or the horizontal axis, as a negative delta x. And if it's, if there's no area, well, then there's no delta x, there's no displacement. So here we have the v versus t graph, the one we just had a second ago. We said this was 4 meters. We said there was no displacement there. And this is minus 4 meters. So if I want to, I can even say this is delta x1, this is delta x2, and this is delta x3. So now I want to move from a v versus t graph to an x versus t graph. Now there's one big thing here, though, that's going to make it a little hard. Notice we are given the displacements, but what was the equation for displacement? Was x minus x naught. But we don't know this from this graph. We are not given the initial position. We are given displacements, but we don't know where it starts. So if we're going to do that, we have to instead be given an initial position. If you're not given an initial position, you can't technically complete this. So let's say the initial position was 0, just to make it nice and easy. So I'm going to start at 0. For the first 2 seconds, I have a delta x of 4 meters. So 1, 2, up to 4. So instead, it should be looking something like that. From 2 to 4 seconds, my delta x is 0. So there is no change in position. So from 2 to 4 seconds, there's no change in position. So stay at the same position. It is now at rest. And from 4 to 6 seconds, we have minus 4 for the delta x. So we're going to go from 4, well, minus 4 would be back to 0. And there we go. And this is now my position versus time graph for this velocity versus time graph. Once again, these are showing us 2 different visualizations of the same motion. In fact, let's double check that we did it right by going backwards. If I have this here, I'm going to have, let's see, what is the slope of this section? Well, it would be 4 divided by 2, so this would be a slope of positive 2 meters per second for 2 seconds. Well, look at that. Positive 2 meters per second for 2 seconds. Then the slope is 0 from 2 to 4. Velocity is 0 from 2 to 4. And then the slope is from 4, this would be minus 2 meters per second for 2 seconds. Oh, minus 2 meters per second for 2 seconds. So what are the final takeaways for working with uniform motion graphs? Remembering that uniform really just tells us that the velocities are going to be in constant velocity segments. Well, right now you should be able to, 1, draw position versus time graph and velocity versus time graphs for examples of uniform motion. 2, we want to make sure we can determine the initial positions and initial velocities from these graphs, from the vertical intercepts. And 3, we need to be able to move back and forth between the two for the same uniform motion. If we have a position versus time graph and we're trying to get to a velocity versus time graph, we look at these slopes. The slope of an x versus t gives us the velocity. And if we're going from a velocity versus time graph to a position versus time graphs, we look at the areas under the graph, which is the area between the horizontal axis and the graph, because those areas give us the displacements.